Kinetic energy. The name kinetic energy translates from the Greek and it's energy of motion. And as the name would imply, you have to have motion in order to have kinetic energy. Kinetic energy, and I oftentimes write it as E sub k, is 1/2 mv squared, where v is the speed and m is the mass. That implies that kinetic energy then is a quadratic, and so goes up non-linearly. Suppose a 300 kilogram package on the roller conveyor belt system is moving at a half meter per second. What is its kinetic energy? Well, E sub k is 1/2 mv squared. 1/2 times 30 times 0.5 squared, 15 times 0.25, which is equal to 3.75. Now, the units, you've got a kilogram, meter squared per second squared. Well, that's the same thing that we had a minute ago for work, because this is going to be a Newton meter, which is a kilogram meter times meter, or meter squared per second squared. So, in fact, energy is a form of work, and so the unit is just like work, it's joules. Okay, suppose that you push on the 30 kilogram package, same one, through a constant force of 120 newtons through a distance of 0.8 of a meter, and that the opposing friction force averages 5 newtons. Okay, now notice this is just a situation. Okay, what work is done? Well, against friction or in total. So if you're talking about against friction, so let's just say AF, against friction. So it's a 5 Newton force through a distance of 0.8 of a meter. It's 4 joules. But that means, since we have 120 Newton force total, if we said we applied 120 newtons that way, and 5 of those newtons were overcoming friction, what happened to the rest? Well, so that work, which is going to be 115 newtons applied still over 0.8 of a meter, is 92 joules. Well, where did those 92 joules go? You used 4 joules in overcoming friction, so your total is just the two added together, or 96. Now, the 96 joules expended, 4 were used in overcoming friction, and the other 92 were used in changing the nature of the motion of the package. In this case, it went into kinetic energy. So we could then use this. So this was opposing friction. We could use then this to accelerate the object, which is what it's doing, which means the object now has kinetic energy. So if you want to find the speed of the package using the energy concepts, you know that it was 92 joules, 1/2 mv squared, 1/2 times 30 v squared. So that's 15 v squared is 92. If we divide the 92 by 15, we have v squared is 6.13 approximately. And then the square root of that is going to give us a speed of about 2.48 meters per second. Now, That's the speed that would have 92 joules. What that tells us is, since you started pushing with that constant force, the presumption is it was at rest, and so now it has speeded up to 2.48 meters per second. If we look at gravitational potential energy, this can be thought of essentially as any potential energy is energy of position. And since it's based on position, this means it's in a gravitational field. So what does that imply? Well, what that implies then is based on the position in the field, we have a force, and we can write that, oftentimes it's written as an H. I sometimes will write it as a D. But it tells you then that this is linear. Now, let's say we're measuring our potential energy from this line. That means that's linear. If you were to go below that line, then you could have a negative energy. Negative energies are possible because you have any sort of potential has to have a reference level or a reference position. And so if we're thinking about gravitational potential, we are below the position. If you were to say, for example, that we were going to measure the position of the ball from the surface of the table. Okay, great. If the ball is on the floor, which is below the table, then that would imply negative potential energy. Well, then that sets us up for this idea of a gravitational potential. A gravitational potential is the energy per unit mass. In other words, we're having a GH or G delta Y or a GD or something like that. And the gravitational potential difference is simply, actually a GY here, is simply going to be from one position to another, and that's going to be a G delta Y or a G YF minus YI. So what that tells you is, depending upon the mass and depending upon the change, this is an indication of the strength of gravity. If we're looking at almost a stereotypical situation, the problem that we look at is a roller coaster. Depending upon where we set our reference level for our potential energy, if we set it here, if we say that the potential energy there equals 0, that means at this lower point, the potential energy is actually less than 0. And then above that would be greater than 0. Now, in this case, we're going to ignore any sort of frictional forces. At the top, it is at rest, V equals 0. Well, it has a gravitational potential energy of mgh or delta y. It has a kinetic energy, 1/2 mv squared, that's equal to 0. So the total energy is potential plus kinetic. Now, if work is done, you would also add work into that. So in the beginning, you have mgh plus 1/2 mv squared. This is the before. The after is also going to be an mgh plus 1/2 mv squared. But I'm going to call these I and F, and I'm going to call this I and F. The mass isn't changing, and we're not looking at a large enough difference in height to have a change in gravitational acceleration? Well, as we can see, it doesn't really matter what the mass of the roller coaster is. That's a common term in all the terms, so that'll be gone. At the top, it's at rest, so this whole term, in fact, goes to 0. Since we defined our reference level of potential energy at the 20 meter below the top, then that means this is all 0. So now we have GH is equal to 1/2 VF squared. 2GH is equal to VF squared. The square root of 2GH is equal to VF.